Welcome to the lecture, Making New Rocks from Old, Metamorphism and Metamorphic Rocks. In this video, I will be describing the formation of metamorphic rocks and how you can go about looking at the different grades of metamorphism, the environments of metamorphism, and then I want to focus on using graphical analysis to kind of determine which type of rocks will form under specific conditions. Okay, so what are metamorphic rocks? Metamorphic rocks are nothing more than rocks that have been altered from a pre-existing rock into a new rock. That pre-existing rock, of course, is referred to as the protolith, and through the process of heat and pressure, it is changed into a new rock, a metamorphic rock. Okay, chemically active fluids will also result in the formation of new rock, and so what you really have to understand is metamorphic rocks take a pre-existing rock and change it into a new rock. Okay, so the first thing I want to address is grades of metamorphism. Whenever you start talking about grades of metamorphism, this means nothing more than you're taking and increasing the amount of, oh no, come on. Hello and welcome to the lecture, Making New Rocks from Old, Metamorphism and Metamorphic Rocks. In this video, I will be discussing the formation of metamorphic rocks, as well as the grades of metamorphism and the different environments in which metamorphic rocks actually form. So, our first question is how are metamorphic rocks actually made? Metamorphic rocks are made by adding heat, pressure, or chemically active fluids to a pre-existing rock called the protolith, and through the process of metamorphism, it is actually changed into a new metamorphic rock. Now, as you add this heat, pressure, or chemically active fluids to the rock, please realize that you are in a sense recrystallizing the minerals that make up the rock and generating that new rock, but you are not going through the process of melting it and making it into a new rock, as that would be an example of an igneous rock. So, the first thing that we want to address is we want to look at the grades of metamorphism. Whenever I talk about grades of metamorphism, what I really mean is the extent to which metamorphism has occurred on that pre-existing rock. So what we have is we have low, moderate, and high-grade metamorphism that takes place. So if you look in this environment that's depicted here, what you will notice is to the far left, we have some burial metamorphism going on. So in other words, this rock was buried. Let's say that this started out as the sedimentary rock shale, and it was buried to a depth of about 8 kilometers. Well, at that depth, you start to get the temperatures increasing, which is going to take that pre-existing shale, and you're going to turn it into the new metamorphic rock of slate. As you go inwards, though, you're going to notice that the grades of metamorphism are actually starting to increase, so because the pressure is, of course, increasing. And so what you could end up doing is you're going to end up taking this pre-existing slate, and then you're going to make it into phyllite. Phyllite can be made into schist, and schist can be made into gneiss. Okay, and so that all has to deal with the grades of metamorphism. What is the extent of which metamorphism is actually occurring? Okay, so you've got way more metamorphic environment down here, so you're going to actually alter the rock even more than you are throughout these previous three. So how is this depicted on a graph? Okay, so whenever you start looking at these graphs and you're trying to make the relationship to which rocks are actually being formed under according to these conditions, we notice that here we have some minor burial, okay, because everything is the focus of temperature and pressures. So at a depth here of about 3 kilometers, we know that we are not going to have metamorphic conditions. So this is going to actually form not a metamorphic rock, but rather it's going to form pretty much a sedimentary rock, and that's going to give us like something like shale under these conditions. Whereas if you go over here, you see here at the terminus of the arrow, we're down at a depth of 15 kilometers and temperatures of about 550 degrees Celsius. Well, those are metamorphic conditions, and those are very, very high metamorphic conditions. Okay, so what you're looking at there is you're looking at the formation of a high-grade metamorphic rock. Whenever you go over to C here, what you're going to notice is the terminus is into the liquidus stage. So you're not even making a rock here, you've actually melted the rock. So under these conditions, you have actually made magma. And then finally you go over here and you see that the rock was actually melted, but then it came back out and it became a solid. So the liquidus crystallized, and so this depicts the formation of a igneous rock, probably being that the terminus is here. This is going to be your igneous rock, either gabbro or granite. So that's how you can use graphs to actually interpret the conditions under which metamorphic rocks and other types of rocks are actually made. Next, I want to cover the different environments that we're going to be looking at where metamorphism actually occurs. Our first environment is, of course, going to be regional metamorphism. Okay, whenever we use the term regional metamorphism, this is basically where plate tectonics is the predominant process that is actually generating the heat and pressure needed to make metamorphic rocks. So as you can see here, through the collision of these two continental plates, you are going to generate a lot of heat and a lot of pressure. And so the rocks that were pre-existing in this environment are going to be altered into new metamorphic rocks. And so anytime you have plate tectonics going on where you've got the collision of plates occurring, that's going to create the metamorphic conditions to create metamorphic rocks, and that's referred to as regional metamorphism. Up here you're going to see a type of metamorphism referred to as subduction metamorphism, but we're going to discuss this one later because I have a better diagram that really shows the conditions that's going on within there, within that environment. Our next type of metamorphism is what is referred to as contact metamorphism. This is easier described as simply baking the rock. So as this magma comes up and the heat is generated to the pre-existing rock, that rock is then baked and turned into metamorphic rock. Those baked rocks are referred to as the areole. And so what you can see is that you're just simply baking and changing the rock through heat in this environment only. Our next type of metamorphism is going to be our hydrothermal metamorphism. This one is easily explained as basically water, hot water that will be chemically active, and as a result it will also kind of in a sense bake and alter that rock as the water percolates into the new crust, and so you get that hydrothermal action that is changing that pre-existing rock. Burial metamorphism. Burial metamorphism starts to take place at about the depth of about 8 kilometers. As you can see, we're nearing the metamorphic conditions at that depth. So this is where you're going to get your low-grade metamorphism, as I demonstrated in the graphs. And so as you continue to go deeper, that rock will continue to experience greater metamorphic environment. And as a result, it will continue to be altered more, transferring from a low grade, as you see here, this is low grade metamorphism, and as more and more burial occurs, you end up getting high grade metamorphism. As I mentioned earlier, this is a diagram that I wanted to use to demonstrate subduction metamorphism. So as you know, the basaltic plate, the basaltic oceanic plate, when it subducts, is actually going to have a lot of water in it, and then as a result you're going to get some, in this region you're going to get some moderate grade metamorphism where you're going to transfer that water into the basalt and you end up getting serpentinite, the metamorphic rock of basalt. Okay, and so the one key thing about serpentinite is it needs an extensive amount of water to be made, and so that's why it tends to form in these types of environments. So that's a key thing that's unique about serpentinite, is how much water is actually needed. And here on Earth, that takes place with at subduction zones generating that serpentinite. Our next to last one is what is called impact metamorphism. Of course, as a celestial body hits the planet, what's going to end up happening is it's going to generate a lot of heat and pressure at that impact site, and as a result, you're not going to be really able to visibly see the metamorphism within the structure itself. But if you were to take some core samples, what you could notice is you may see some impact melt along the floor of the impact structure, but it's really whenever you start to dig in deeper that you're really going to see where a lot of the metamorphism has actually taken place. So in other words, to identify impact metamorphism, you're really not looking for specific features that indicate the metamorphism has occurred. You are more looking for specific types of rock that are present to indicate that metamorphism has occurred. And as you can see here, melt rock, hydrothermal selenite, which is just a form of gypsum. Selenite is kind of like the impact equivalent to gypsum. Swavite is kind of impact breccia. Shatter cone is one of the big indicators that you've had an impact event occurred. So that's something that I actually have samples of shatter cone myself, which is kind of like the smoking gun for if you find an environment and you find shatter cone, that's one thing you definitely want to see to indicate that, yep, it was definitely an impact that actually created this structure. And then shocked gneiss. Now, of course, there are some other things that you could look at, things like coesite or shocked quartz. Shocked quartz is the #1 indicator of an impact event because there's no pressure here on this planet that can actually alter the structure of quartz. Only an impact can do so. And then our last type of metamorphic environment is, of course, going to be dynamic or fault metamorphism. And so as you see the fault move and slide along the surface, so you've got sliding right along here, caused by, of course, the fault motion. What ends up happening is you can slightly metamorphosize the pre-existing rock, as you can see here, and this is a special rock referred to as myelinite. And so the presence of this myelinite is an indication that this looks simply like a crack here, but because of this presence of myelinite, you know that this rock is actually moved, generating heat that has actually, created this rock. So you've got some metamorphic rocks found along this area, specifically myelinite. Also, look at the offset. So it's kind of like you're always looking for a clue of, okay, you see this on a road cut, and you're like, okay, what happened here? And then you say, oh no, there's the rock. There's the offset of rock layers. This indicates that some sort of event took place where the rock structures were actually moved, and as a result, it created what you visibly see here. So hopefully this explains how the formation of metamorphic rocks and how you can have different environments and different conditions to make different metamorphic rocks. This concludes the video, and if you have any questions, please do not hesitate to email me.